Okay. So what you're looking at is a histology slide of the thymus and kind of the cartoonified version of that. But there's two main regions of the thymus that you need to be aware of. One of them is the thymic cortex. This is generally the outer band part of this, the darker staining stuff on these histology slides. This is where a lot of our initial T cell development and training is going to occur in terms of being able to at least recognize MHC. Then, to be able to distinguish self and non-self, your cells are going to move from the cortex into these little more innermost sort of pockets that you see that are called the medulla. The basic process for this is cells come into the thymus from the bloodstream and they enter through basically the medulla and the corticomedullary junction. You do know how to pronounce that word. That big word, corticomedullary junction, that just means the border between the cortex and the medulla. You find a lot of blood vessels in this area, so your cells come in from those blood vessels and enter at this sort of boundary, at this border. And then they migrate out toward the edges of the cortex. As they mature, they're going to kind of do a loop around the cortex and back, ultimately, hopefully, to one of the medulla regions, whichever one happens to be closest to them for their final maturing process. So we saw this figure back in like chapter 2, but it's kind of good to revisit it. Cells are actually going to spend 1 to 3 weeks in the thymus going through this process. So it's not a fast process. This is actually relatively slow, all things considered, in the body. They'll pass through a series of really well-defined stages as they go through this process of training and maturing. And then ultimately they will find their way back to a blood vessel and they will leave the thymus entirely and travel out to the lymph nodes where they will look for antigens and antigen-presenting cells. Okay, so structure of the thymus, just as a revisit and a slight enlargement over the last slide. These darker staining areas out around the periphery are the thymic cortex. You'll notice that that takes up the majority of the space in the thymus structure. And then you've got these smaller, lighter staining, less dense areas toward the center, and they are lighter in pink, and they take up, what is that, maybe 1/4 of the space in the thymus? Rough estimate. 1/5 maybe. The T cell precursors start off at the borders here when they come in through the bloodstream. They migrate out to the periphery of the cortex, and eventually they will loop their way back into the medulla. They'll spend some time circulating around in here, and then they will exit the thymus altogether. So if I were to draw that for the people joining from at home, that means that the cells kind of enter through. To the recordings, I can make those more available. They take a little while to render in post. And it doesn't like to let me go back. Okay. I'll try to remember to draw on the screen a little bit more today than with my finger on the board. So, when a thymocyte enters the thymus, let's backtrack. The hematopoietic stem cell precursors that give rise to all of our different types of cells, those exit the bone marrow and they migrate toward the thymus. Once they get to the thymus, they are still what are called double negative cells. Double negative means that they do not express either CD4 or CD8. At this point, they're just called thymocytes. They're not helper or cytotoxic yet. They haven't committed to those lineages.
So you said it's a hematopoietic stem cell.
Yes.
When it goes to the thymus, is that the moment where it is called a thymocyte?
Yes.
Okay.
Basically, once it gets to the thymus and gets in the thymus, that's when you would call it a thymocyte. Ultimately, our goal is to get them from being double negative cells. They will pass through a temporary time period where they're double positive and they will express both CD4 and CD8. But ultimately, we need them to commit to one of those two types, either CD4 positive helper T cells, TH cells, or cytotoxic TC cells, which are CD8 positive. They have to pick one. They can't stay both. If you isolate lymph nodes from a mouse or a human or whatever, you should not find double positive or double negative T cells. They should be either CD4 positive or CD8 positive. All right.
The negative ones, are they the ones that get neglected?
The double negative cells, no, that's actually a normal stage in their development. They all start off double negative.
But at the end, they have to.
But the end, they need to commit to one of those lineages, yes. There is an alternative option depending on the path that they take, and I will talk about that too. So.
But it won't become negative in the envelope?
The end cells, the only ones that do stay double negative for CD4 or CD8 are the gamma delta T cells. And I'll talk about those too when we get to that stage in their development. So the final screening of cells, once you've kind of generated all of these, like I said, they spend some time, they initially migrate in from the boundaries of the medulla, then they migrate up and spend some time around the edges of the cortex until eventually they work their way back to the medulla. Then they'll spend a fair amount of time running around in the medulla. And by a fair amount of time, I mean several days up to like a couple weeks. What's going on in that is you're removing the autoreactive or self-reactive T cells. Then eventually you get them released into the bloodstream and they exit the thymus altogether. During this process, you also have to generate a functional T cell receptor. So genetic recombination for your T cell receptor alpha beta chains or your gamma delta T cell receptor chains. And we will briefly kind of review a little bit about how that worked in case you have forgotten from the previous chapter where we talked about development of the B cell receptor and briefly a little bit about the T cell receptor.
What are you talking about, evolved T cells?
We're talking about developing T cells.
Also,
These are still thymocytes. Yeah.
naive T cells.
Naive T cell means it is a mature T cell, but it has not yet encountered antigen. So there's specific usage for that.
You said the final screening happened in the medulla.
Yes.
Okay, cool.
Final screening happens in the medulla.
That makes sense.
Sort of. As much as any of this makes sense. Our lymph nodes share a very similar architecture, and so does our bone marrow. So we'll see this pattern of having a medulla and a cortex sort of region and these little special spaces kind of defined as microenvironments. We'll see that repeated in the next chapter as well when we look at bone marrow and B cell development. Okay, so that protein that you see there is Notch, N-O-T-C-H. Notch. This protein is required for hematopoietic stem cells to become T cells. This is actually part of the intracellular domain of it. It's a neat pattern. I'd never seen a protein that quite looked like that before, so I thought I would just stick it in.
Required for what?
It's required for stem cells to become, the hematopoietic stem cells to become T cells.
Is the alpha helices on these all the same?
They're really similar, yeah. What you've got are multiple chains that are interacting, so multiple pieces, like this is all part of the same protein. As far as I'm aware, I think these are all parts of the same protein.
That's so cool.
And multiple domains, yeah. It's definitely, I love looking at protein structures in general, so I just kind of wanted a graphic for this slide, and I figured it might as well be a relevant one. Because Notch is the first thing that's going to start telling those hematopoietic stem cells to differentiate and start to become T cells. This is our first signal that basically turns off other pathways. After this signal is received, after Notch signaling, The cells no longer become B cells, they don't become dendritic cells, they don't become NK cells, they don't become other things, they become T cells specifically. So this is our first T cell specific signal.
Dr. Steele?
Yes.
So the notch, that's in the bone marrow? And it's
The bone marrow, it's in particular, it's in the thymus. Notch is found in
So
the
they've
thymus.
already-
Notch and notch signaling is in the
they've already
thymus.
moved from the bone marrow
They've
to
already
the
moved
thymus, and
from the
that
bone marrow to the
activates
thymus.
them to become T
And
cells.
this causes them to start differentiating into T cells. Yes.
Okay, thank you.
So could it change its mind once it gets to the thymus before it's interactive with Notch and be like, I actually want to be a dendritic cell? Could it like just go and do that? Is that possible?
Theoretically, yeah.
Cool. But once you have Notch, it's done.
Once you have Notch, that process becomes not entirely irreversible, but close. What type of T cell this is going to become, that's another story. So these hematopoietic bone marrow precursor cells, before they get to the thymus, they still have the ability to become any of your blood cells. Red blood cells, white blood cells, fill in the blank blood cells, like we talked about all of the different types. They could become granulocytes, they could become antigen presenting cells. There's a bajillion different options, and we've learned about what those are. But this receptor known as Notch commits them to the T cell lineage. So once they start receiving Notch signaling, they become T cells, and it's exclusive to T cells. If you take away Notch, these will develop into B cells and other types of cells, but mostly B cells. You do need some supplemental growth factors in this process. Interleukin 7, IL-7 is one of those. FLT3L, FLAT3 ligand is another one. We're not going to worry too much about those growth factors. But Notch binding by itself is enough to get these cells to commit to becoming T cells in vitro. We had no real problem getting hematopoietic stem cells to become B cells when we were isolating bone marrow and trying to grow up an immune system in vitro. B cells were easy. They just did that automatically. There was no additional signaling that was really required other than some basic growth factors. So B cells are kind of the default. It's this Notch signaling that really causes them to become T cells. And again, as the cells exit the bone marrow, they're still double negative cells. So these do not express CD4 or CD8 at this particular time. They also do not express a T cell receptor yet. So these are naked babies. They have a lot of growing up to do.
So if you were to get a bone marrow transplant, would that mean that you would have a whole new set of variety for genetical antigen presenting stuff?
Yes, people who have bone marrow transplants have whole new immune systems that grow up.
That's
kind of cool.
Yeah, that's actually why bone marrow transplants are used as treatments for leukemia and other blood-borne cancer-related illnesses. If you're wondering how a bone marrow transplant is performed, it's done in mice. It's actually pretty simple. It's not much different in humans. First, they give you a dose of radiation. This is a lethal dose of radiation. It will kill you, period. First, you kill yourself. Awesome. That's a lovely day, I'm sure. They give you this lethal dose of radiation. It's a strong dose of radiation. The point is to kill off all of your existing malfunctioning bone marrow. Then they acquire bone marrow from a donor, and historically that was done by taking it out of your hip, basically, because you've got a nice big strong bone there that's got a lot of bone marrow, so they stick a really big needle. You're under anesthesia, so you don't feel this, but they stick a giant freaking needle into your hip and they suck out your bone marrow with a big syringe. It's not a super sophisticated procedure. Then they take that bone marrow and they inject that into the donor, or the recipient, sorry, rather, because that was the donor. Interestingly, in mice, you can basically just give that through an IV infusion. You don't have to re-inject it into the bone specifically. You can just inject it into the body. Those cells will migrate directly to the bones and set up housekeeping all on their own.
So you said traditional.
Why? Lots of signaling molecules are involved in that process.
You said traditionally you just suck it out. What did they do now?
I don't know what they currently do, but I'm hoping that technology has improved a little bit and we have some additional purification procedures and stuff. I'm hoping, yeah, because that's kind of scary. I'm on the bone marrow donor registry, so I did look up what would happen if I ever got called.
So the reason they radiate, I mean, there's something wrong with your immune system. Is one of the reasons they kill it with the radiation so you don't react to like a normal transplant. Your body may react to it.
It's mostly because the cancer of the blood that you have is something that is occurring in your bone marrow, and there's no other effective way to treat it.
Okay, so they're just irradiated.
Yeah, we just have to kill it all and start with a blank slate. Yeah.
Okay.
Again, for this, you really do want to have a close tissue type, so your MHCs do want to match as much as possible. All right. So, because these cells have literally nothing, no CD4, no CD8, no T cell receptor, at this point, like I said, they're naked little baby cells. This is the first of the 4 double negative stages. So there's kind of 4 substages to being double negative. Right now, incoming T cell or incoming thymocytes, they're not even technically T cells yet. We call them thymocytes. They don't have a T cell receptor. That's the bare minimum to be a T cell. You have to have a T cell receptor. Kind of makes sense. Okay, there are 3 other proteins that help to define the various 4 stages of being a double negative T cell or T cell progenitor, something that's supposed to become a T cell. The 3 other ones are c-KIT, which is CD117. This is a receptor for something called SCF, stem cell growth factor. Because these cells are going to have to go through some proliferation. There's another one, CD44. This is an adhesion molecule. It is important for adhesion in the thymus. This is how your thymocytes stick to other cells in particular. And CD25. So I told you we had CDs coming, lots of different CDs. There's at least 117 of them. Check it out.
Do you memorize these?
There are, what?
Do you memorize them?
Do you memorize these? You should know these. Yes, you should know these. These are important to understanding the process through these 4 stages. CD25 is the alpha chain of the interleukin-2 receptor. So when these cells first get to the thymus, they are CD117 double positive, which means they express high levels of CD117. There's just a lot of this on the cell surface. That's all that tells you. They also express regular normal levels, positive, meaning it's detectable levels of CD44, but they do not express CD25 when they first arrive at the thymus. This is what they look like when they're in transit. So if you take a blood sample, if your blood sample is big enough, you would capture a few of these cells. Maybe, I don't know, 3 to 10. If your blood sample is big enough, call it a pint. There should be at least a few of these in there. And this is what those cells would look like when you started to look at what surface molecules they express. This is known as the cell's phenotype. Oh, that lovely word from intro biology and genetics and evolution and stuff. You had genotype and phenotype. This is the phenotype.
Cool.
This is what's expressed on the surface. Okay. Your cells have arrived at the thymus. You now have thymocytes. Yay! We progress to DN2, double negative stage 2. This is where you start rearranging your T cell receptor. Now, there were 2 types of T cell receptors. There were the alpha beta T cell receptors, and then there were the gamma delta T cell receptors. And I'm betting you've probably forgotten anything about those at this point. So, the alpha beta T cell receptor type is the main type that we deal with because it's the vast majority of cells. There's some actually good reasons for that. The gamma delta T cell receptors are less common. They are less than 5% of cells, so we don't see nearly as many of those. So the double negative 2 stage of cell development, you still express high levels of CD117. You still express CD44. But you also start expressing the alpha chain for the IL-2 receptor, CD25. And at this stage, they're also going to start trying to make a functional gene rearrangement for the T cell receptor with either a beta chain. Option 1, you can make a beta chain. Option 2, you can make both a gamma and delta chain. Well, no wonder 95% of them choose the easy route and just do one chain. That's logical. It's also, if you think about all that VDJ recombination stuff, it's much simpler to just rearrange one gene at this stage. Okay, once you actually generate a functional T cell receptor, if it's an alpha beta T cell receptor, if you get a functional beta chain, you move to the double negative 3 stage. In this particular case, expression of CD117 decreases. It drops from high expression just down to normal expression. You actually lose CD44, but you do keep CD25. Cells at this stage start to express their T cell receptor and undergo what's called beta selection. We will talk more about beta selection also. But mostly at this point, your cells express their T cell receptor, whichever one they functionally rearranged. Assuming it's the beta chain, they've got a lot more development to go. But what if you actually made a gamma delta T cell receptor gene pair that was functional and you made a gamma delta T cell receptor, a fully functional one? That's actually where those cells exit this process. Gamma delta T cells do not progress any further. They exit the thymus as double negative cells. Remember, the gamma delta T cells, they were the weird ones. They don't recognize peptide antigen, they don't have a requirement for MHC, and they don't express CD4 or CD8. These particular types of T cells are involved in detecting non-classical antigens, so normally lipids and stuff. They're more likely to see antigens presented in the context of CD1, to pick up a tidbit from the previous chapter and tie that together. But your alpha beta T cells progress to the double negative 4 stage. At this stage, they basically lose most of their expression of c-KIT CD117. CD44 is already gone, and they would now lose expression of CD25. So all of these early markers, they are pretty much gone at this point. These cells actually, at this point, go through a round of proliferation. They made a functional beta chain. Yay, time to do a ton of mitosis. Or several rounds of proliferation. You're going to make a clone, a large group of cells. For those of you who like Star Wars, a clone army. Yeah, because I'm geeky. Yes, I like Star Wars.
I like Star Wars.
Yes, I also love Star Trek. And Doctor Who. Pretty much all the sci-fi. When's the last time I watched any? Little before the semester started. Right now, my science is actual science. It's immunology. It is not sci-fi. Maybe over the weekend I'll watch something, but I also need to get in a Halloween movie. I have seen 0 so far this year, and that's a problem for me. I have not seen the new Hocus Pocus. That's reserved for girls' night with a friend of mine when we do a virtual girls' night. Yeah. Why virtual? She lives like 300 miles away. So we occasionally like get together and on Skype and we watch a movie together and have some wine, and it's nice. We have not done that like all semester, so it's, been a while. Sometimes we like cook, like bake a cake or something while we do this, so we have fun when we do. All right, so your cells proliferate. At this point in time, since you've made a functional beta chain, the cell's actually going to shut off the gene at the other chromosome, so this is called allelic exclusion. It's going to prevent recombination of another beta chain. It's already done one and gotten it right. Why does it need to do another one? So it just shuts down that chromosome. And you start dealing with trying to get a productive rearrangement at the alpha chain. If you get a productive rearrangement at the alpha chain, you now progress to also expressing CD4 positive and CD8 positive cells, and those become what's called the double positive thymocytes at the end of this.
Those are the ones that express the CD4.
Yes, so double positive means both CD4 and CD8. This table was really helpful to me, so I included it in the lecture.
So why is it called double negative 4?
Because double negatives do not express CD4 or CD8.
But it becomes double positive.
But it becomes double positive at the very end of this stage. This is like the transition to the next
Okay,
phase.
I see.
Yep. So most of its stage is still negative.
Gotcha, okay.
It's just at the very end. If you get a productive alpha chain and you start getting signals through that productive alpha chain, then you start to express CD4 and CD8. I already talked about most of this, but I actually have broken this up into the different sections of the double negative times. So during double negative 2, you've still got high levels of CD117, you're expressing some CD44, and you are generally expressing maybe some CD25 at this point as well. The TCR beta chain rearrangement is one of the first things that takes place, and it's likely to be productive. Your cell gets 2 chances to get this right in terms of making a productive, actually codes for a protein and isn't mutated horribly beta chain. Mutated horribly means it's not going to work. This actually seems to be based pretty much exclusively on speed. Which T cell receptor genes get rearranged fastest and make it to the end point first? So it's not any more mysterious than that. The fate of whether it's an alpha beta or a gamma delta T cell is just based on which genes rearrange first. And since you only have to make one successful beta chain, it's usually going to be a beta chain. Once in a while, you have some super ambitious little T cell that decides it's really just going to become a gamma delta T cell, and it doesn't. Interestingly, gamma delta T cells are more common during fetal development and less common during adulthood. You make most of them before you're born. Again, because you only need one successful recombination event to take place genetically, beta chains usually win. And it's about a 3-to-1 or more than that. Alpha beta outcomes are about 3 times more likely than gamma delta recombinations. We're not sure why gamma delta T cells are more common during fetal development. We just know that this is something we have observed. We think that there's maybe some evolutionary reasons for that, or maybe it's just because of differences in the environmental cues that are being received. So again, if you successfully rearrange a gamma delta T cell receptor chain, the thymocytes are basically done and they exit the thymus, still double negative. They will go on to recognize glycolipids and other unusual antigens rather than peptides in MHC. So that's basically where we are. This is the double -2 stage. We started off as double -1. These are the cells that come from the bone marrow into the thymus. They are CD44 positive, CD25 negative. At double -2, they start trying to rearrange a functional T cell receptor beta chain or gamma delta chain. They express CD44 and CD25. If they actually make a functional beta chain, cool. If they make a gamma delta chain, also cool. But at this stage, they start to express that T cell receptor. They lose expression of CD44. Basically, that's being replaced by, look, I made a T cell receptor. And you still maintain expression of CD25. Then they go through what's called beta selection. Beta selection is really a process that tests these cells and says, is your beta chain receptor actually functional? Can you receive signaling through the beta chain? That's it. That's all that actually means. I kept looking for a better description of it in the textbook, and I didn't really find one. But all beta selection is looking at is, can you get some basic pro-survival signals through this pre-T cell receptor? At this stage, it's usually made with a temporary placeholder alpha chain, which is why it's called a pre-T cell receptor. Temporary placeholder alpha chain.
So it's saying basically, like, can that T cell receptor or the pre-T cell receptor receive any sort of signal? Like, can it?
Yes. Yep. It's just testing whether or not this T cell receptor can functionally signal or not.
Doing a mic check.
Mic check. Good way to think about it.
And the other ways.
Okay. Assuming beta chain rearrangement is successful or beta selection is successful, the cell then needs to actually get a real alpha chain instead of its temporary little placeholder alpha chain. You stop recombining more beta chains. That's allelic exclusion, again, because you've already done a functional one, so there's no need to try to rearrange the other gene. You go through a round of mitosis at this stage. So proliferation is definitely something that is a product of successful signaling through that pre-T cell receptor with the temporary placeholder alpha chain. And it starts to stimulate expression of CD4 and CD8 co-receptors. Those don't really come up fully until you've got functional signaling through that pre-TCR and then through the mature T cell receptor. So the double -4 stage, DN4, that is where you go through this T cell receptor alpha chain rearrangement. Assuming that is successful and you go from your pre-TCR to a fully functional T cell receptor, you stop being a double negative T cell and you progress to being double positive. So it's actually signaling through this complete T cell receptor that leads to expression of CD4 and CD8. Those cells then have to go through positive and negative selection in the thymus. And both positive and negative selection are intended to make sure that, yes, your T cell receptor can bind MHC and self-peptides, and that no, it doesn't bind with too high an affinity. So we talked about this before a little bit. You have to have the Goldilocks level of interaction in this case. It's got to be just right. If your T cell receptor cannot bind with MHC, these cells will die. You made one, you got a few little pro-survival signals, but if it does not effectively engage with a certain level of strength, then these cells will die of neglect. If it does receive strong enough binding and you get good signaling through this T cell receptor, that acts as a pro-survival signal, and your cells can then actually start to progress to the next stage of their maturing process, which actually occurs in the medulla of the thymus. So in that particular case, they become tested by negative selection to make sure that they're not binding too strongly to self-peptides and MHC, meaning that they would be autoreactive.
They undergo a second negative selection?
They go through one negative selection. Positive selection, making sure it can bind to MHC in the first place and receive a signal. If it does not, it's death by neglect. Negative selection is the next round that occurs mostly in the medulla, and that ensures that you don't have self-reactive T cells.
Wait, I'm confused.
We're going to work through it.
So the death by neglect, that was if they failed positive selection?
Death by neglect is if they fail positive selection, yes. Bless you. Okay, backing up to that double negative 3 stage, so this is where we're at, is the double negative 3 and double negative 4 stage. Remember, these are like fairly well-defined stages, but it's still part of a continuous process. So these cells are CD44 negative, and they will change from being CD25 positive at double negative 3 to CD25 negative at the double negative 4 stage. That's one of the phenotypic changes that we know that these have passed through beta selection and made it through beta selection. Beta selection just means, does this pre-T cell receptor with the temporary placeholder alpha chain, does it actually get a functional signal? So I can't really quite circle as effectively on this as I would like to, but the temporary placeholder alpha chain is this little stubby piece over here on the side. Like I said, I can't circle it as well, but you'll notice that one of those T cell receptor arms has a wing on it. That's the beta chain, and the other one looks just like a stick. That's the temporary placeholder alpha chain. That's for our folks watching the recording at home later, or reviewing later and not remembering what's supposed to be what. So this precursor T alpha chain that gets made is actually, just a surrogate for the real T cell receptor alpha chain. It hasn't gone through genetic recombination for that yet. Assuming you get functional signaling through this pre-T cell receptor, that's what triggers genetic recombination of that real alpha chain, which is in a different gene. And at that stage, you've got a double negative 4. So that's its job during double negative 4 stage, is basically, can you make an alpha chain? You made a beta chain, now can you actually make a functional alpha chain? Most cells that rearrange a beta chain will be able to successfully rearrange an alpha chain. Questions about the double negative stages?
And I need to read it.
Need to read it?
What did you say again that triggers the expression of CD4?
Expression of CD4 and CD8 will happen only after you've got a complete T cell receptor that is receiving signaling. So that'll be when you progress from double negative to double positive at the end of this.
So then the pre-T cell receptor, once it reaches the double positive, is
a full T cell receptor. So in this transition from the double negative 4 to the double positive, you'll notice that your pre-TCR becomes replaced with a fully functional active T cell receptor that's got wings on both sides.
And then is that also where it tests, or is that where they test the functional alpha chain as well?
That tests the functional alpha chain, yes. Assuming you've got a functional alpha chain and a functional beta chain, then you start seeing expression of CD4 and CD8.
So that's when the alpha chain, I know it has the placeholder, is that when it goes through the genetic?
The alpha chain placeholder is only back here in the double negative 3 and 4 stages.
So then it has the actual alpha chain.
So then this has the actual alpha chain, yeah. And they're representing that again. They replaced that one stick with the one with the little arm on it, the little wing on it.
It says something about the
Okay. This is supposed to be the pre-TCR. You said this one was what?
That's the alpha.
The alpha.
That's the placeholder alpha.
After the expresses,
The other one is the regular full beta.
Regular. Is it a full?
Yeah.
Gotcha. Thank you.
Okay, so this last part over here is progressing from our double negative cells to our double positive cells. Once you get that expression of a real alpha chain, it replaces that temporary placeholder alpha chain. You get a fully functioning, mature T cell receptor. Yay, you did your genetic recombination correctly. This signals the cells to start producing both CD4 and CD8, and those cells are now known as double positive cells. Sort of the next phase in this process is to go through positive selection and negative selection and try to produce cells that are single positive for either CD4 or CD8, but not both. So this is kind of the final stage of maturation when they shift from being double positive to single positive cells. So at this point, you might be wondering what causes them to pick either CD4 or CD8. How does it choose? It is a big decision. But before we actually worry about exactly how that decision gets made, because I don't know if I'm actually going to make it quite that far today, positive and negative selection are important. So our double positive cells, this is 80% of the thymocytes. The vast majority of them make it to the double positive stage and undergo thymic selection. So you've made this big, vast pool of cells. They've been through a few rounds of mitosis. You've got several thousand copies of these things at this point. That's 80% of the cells in your thymus. For the thymocytes, the first step is positive selection. This is where you select for the thymocytes, the double positive thymocytes that have receptors that are capable of binding self-MHC molecules with at least low affinity. (95 to 98% of the cells you just generated flunk this first test and get killed. It's harsh. You think tests in college are harsh. That's nothing compared to what goes through your thymus, where 98% of the cells fail. It's worse than trying to get into med school. You'll be much more likely to be successful at getting into med school than you are to actually have a cell get through this process. The point is that the T cells have to be able to recognize those peptides on MHC. If they can't do that, they're not functional T cells, or they'll never be functional T cells. They'll never be able to respond to antigen. So this is your first pass. Eliminate all the cells that can't functionally do their basic job. Next comes negative selection. Negative selection is going to eliminate the cells that have high affinity receptors. So you want low affinity, but it'll basically take any affinity at positive selection. It's like, look, you can bind self-MHC. Cool, you pass this part. The negative selection eliminates any that bind too strongly. So again, this is to screen out the autoreactive or self-reactive T cells, that basically the ones that bind and don't let go. Another 2 to 5% of the remaining cells, so 2 to 5% of the cells fail this. Actually, that's actually pretty good. Of the 5-ish, 2 to 5% you had left, 95% of those actually succeed at the second test, if you make it through the first test.
So how did those cells die when it's like...
It's called death by neglect. They don't receive pro-survival signals, so they basically hang out there for up to like 3 weeks or so, and if they still don't get any survival signals, they just die by apoptosis.
And then for the other one, is there like any, so like for those in negative selection, because you said positive selection was death by neglect.
Positive
right?
selection is death by neglect.
And then negative selection.
Negative selection is also apoptosis, but it's directly induced because of too strong a binding. The mechanisms for that are less clear at this point. I get to say that a lot in this class. Basically, we don't know yet. Or we've got some clues, but it's not fully clear, or there's conflicting evidence. So our immune system depends on the gamble that at least one out of the millions of T cells that you make that have a randomly generated T cell receptor will survive this positive selection and the negative selection and make it to your daggone lymph nodes and hopefully be useful in a particular infection. However, there's no guarantee that any T cell you make during this process will be useful for any particular infection that you get. You may just not have one that protects you against COVID or flu, since those are currently the two things mostly circulating. Or in my case, whatever the heck is causing my kitten to have diarrhea. No, it's very no bueno. it's muy malo. There is no gut microbiome left. Those things are squeaky clean inside. Poor little guy. And he's on veterinary medication for it, and it has not cleared up yet. So I've got another phone call out with my vet going, now what? We tried the obvious thing, and you used to give him kaopectate, but now you can't do that anymore because they reformulated kaopectate that contains aspirin, which is toxic to cats. Just so you know, cats should not have aspirin. Fun things I learned this morning. Not that I ever gave them aspirin. Basically, cats are weird, don't give them medications. If it works on a dog, do not assume it will work on a cat. Pretty much assume it'll be toxic to your cat. All right. Moving on. So what happens during this process of thymocyte maturation and positive and negative selection? Thymocytes are learning basically MHC restriction. They are being tested to make sure that they can recognize MHC first and foremost, and that they don't do it too strongly, secondly. Basically, we do not want the gonzo autoreactive T cells. So they did this experiment in mice that kind of really illustrated this principle. They took some strains of A mice and B mice, they crossed them, they made AB mice, those are the F1 ones, and then they gave those irradiation to wipe out their immune systems. Then they got a thymus from one of the parental mouse strains from a B mouse and stuck that in the mouse. So now it has a thymus. The mouse itself, its tissue type was AB, but its thymus is only B. And then they got bone marrow from a sibling AB mouse to reconstitute. And then they looked to see what kinds of T cells got made. And it was interesting because we know that the rest of the body is AB, we know that the bone marrow is AB, but the only type of T cells that actually got made were B type from the thymus. A types never actually came out of the thymus. So we know that this is an important process for our cells being able to recognize our personal MHC. And it has to be personal or very closely related. They took this a couple steps further and they actually tried infecting these mice with a particular set of viruses. And they found out that the immune systems of some strains of the mouse did not survive, and immune systems from other mice did survive, and that was dependent on what type of immune system they had used to reconstitute with. The particulars of that, you can learn about that in graduate school. Like, we don't need that for an intro immunology class. Normally, these are a natural match. MHC and your thymus are normally a natural match because, well, it's all part of your body. That's the way things are supposed to be. They're from the same organism. The only time you run into problems is if you have a bone marrow transplant or a thymus transplant, or another organ and tissue transplant later as an adult. This leads to graft versus host disease. And in this case, graft refers to the grafted bone marrow. because that goes back to a question you had before. It's not just a graft of any particular tissue. The graft versus host disease basically means the bone marrow transplant starts attacking the organism in which it was transplanted.
It's a nasty
I did look that up.
disease.
It is nasty.
You'll die if you get like the wrong graft. So like with transfusion associated, like with blood graft versus host disease, you die within like 4 weeks. Or
I'm
something
surprised it takes 4 weeks.
Yeah, I think that's the long one.
Yeah.
It's pretty bad.
Yes.
What does F1 mean again?
F1, that is your filial 1 generation. That means that's the resulting cross between 2 parental strains. Yeah, first generation. Child. Okay, that positive selection process generally takes place in the cortex of the thymus. So as the cells have kind of looped out and they're up around the peripheral edges and away from the medulla, that's where you see most of the testing for, can you at least detect MHC somewhat? This is the positive selection part of the process. And they're testing against specifically the cortical thymic epithelial cells. And in your textbook, you see this abbreviation a lot. It's called the CTEC. CTEC, cortical thymic epithelial cells. These cells are weird. The thymus is a weird organ. They're weird because they express MHC class 1. Okay, that's totally normal. All cells in your body express class 1. But they also express unusually high levels of MHC class 2. So you're testing for a fit between the T cell receptor that your T cell just recombined and either MHC class 1 or class 2. The developing T cells sort of browse the possible MHC class 1 and class 2s, look for can they detect or recognize at least one of them somewhere, somehow. Browsing in this context basically just kind of means that the cells form these temporary interactions and they roll around in there. So as these cells sort of roll around, they're going to gradually encounter different thymic cortical cells, and they'll be able to temporarily bind to one and go, oh, look, I got a pro-survival signal. Cool. Can I do it again? And they'll roll off to another cortical thymic epithelial cell and see if they fit with that one. The more pro-survival signals it receives, the better. The more likely it then is to be able to actually progress to the negative selection part of the process.
Is this happening when you said that they, when they kind of circulate the medulla?
Not the medulla, not yet. This is still in the cortex. Yeah. Cortical thymic epithelial cells. Yep. Cortex. As opposed to the medullary medulla.
So if
cells.
it's not, if its pro-survival signal is not working, will it still keep trying?
It'll keep trying. It's got like a few weeks to keep trying. Yeah. It's not an immediate death sentence if it doesn't recognize the first MHC it comes across. It's got like up to 3 weeks to find potential match. If it doesn't find some MHC within 3 weeks of rolling around in the thymus, it's pretty much done. Yeah, it's just gonna go through apoptosis. It's just gonna be like, well, I guess I'm not wanted. Death by neglect. That's exactly what that is. The cells that bind too strongly, those don't always make it out of the thymus either. If it binds too strongly to your MHC, you'll still get apoptosis that occurs. It's only the cells that have that just right binding that's usually called the Goldilocks zone. They even use that term in like space exploration. The Goldilocks zone is like the zone of habitable conditions for a planet. Similar to Earth. Places where we could survive and thrive. And I was wrong. In my notes, it's actually 3 to 4 days, not 3 weeks at this point. Okay. So positive selection ensures MHC restriction. That's its main job. It makes sure that the cells can actually detect MHC and can bind with at least some degree of appropriate levels of binding to that MHC. Negative selection is going to be covered on the next exam because we are now out of time. But we made it through half the chapter. Not bad. So we'll finish up on Thursday of next week. Tuesday of next week, we have the exam, which will cover chapters 6, 7, and up through positive selection in thymocyte development.
So we should learn positive selection?
You should learn positive selection, yes.
Will this be a similar style to the first exam?
Yes, it will.
Cool.
I have a good question. So you know autoimmune suppressants, right?
Yeah.
Okay. So it slows down your immune response. It doesn't shut it down. It slows it down, right?
Depends on the drug and how it works.
That's what I'm trying to figure out because
So prednisone is, for example, is one of the common ones that's an immunosuppressant, and it's used pretty liberally in medicine today. If you have really bad mosquito bites, you may end up on a round of prednisone. It basically squelches production of a lot of the pro-inflammatory cytokines and chemokines and really hampers the ability of your immune system to respond.
okay, that makes sense.
It doesn't, it's not that it slows it down. It doesn't kill it. It doesn't slow it. It just basically stops it from responding and says, nope, you don't need to do that.
Okay. So then when it comes, like, say your immune comes back on, what happens?
Usually you should have cleared the infection, the mosquito bites or whatever triggered your major response should have had a chance to get cleared through the innate immune system, which still works reasonably a little bit through that. But your skin should have had time to heal, and
It'll be okay.
basically it's just normal.
Yeah.
Yeah.
Okay. That makes sense. Thank you.
Yes.
I noticed that my attendance grade went down, but I haven't missed 6 classes. You want me to email you?
Yes, I
Okay.
think you might have already emailed
Yeah,
me.
okay.
Okay. I haven't had a chance to get through emails from today yet, but I will work on those.
Okay.
Hello, I want to talk to you too. Let me deal with other questions. Yes.
Sorry. I don't want to sign in.
That's the main
You didn't get signed in?
goal.
Send me an email and let me know. I can manually log your attendance. Okay, so I was thinking about projects that you could actually do for this class, and one of what I was thinking of partially depends on your interests. Okay. Because that was one of the things that was really explicit about the honors contract. It's supposed to be based on your interests and what are you interested in immunology. So that's what I need to talk to you about is what are you interested in immunology. What I was thinking of is like a project where I ask you to look at either like a vaccine and how does that vaccine actually produce immunity? The whole process. What toll-like receptors will it activate, or what other types of receptors will it activate? How does it trigger your innate immune response? What types of cells should respond? How does it trigger your adaptive immune response? What types of cells would respond? How long does all of this take? Like when do these responses kind of peak and when do they go away? And make me an infographic and a written summary.
So we do like kind of like a presentation going through all the steps. Okay.
Yeah.
That'll be fun. I like that. Yeah.
Yeah, and you can work together on that.
I like that.
You like that? Okay, so pick a vaccine.
Oh.
So you get to choose. You can use any type of vaccine that's available. You can actually even go for Ebola vaccine since there's currently an Ebola outbreak. I just wanted something that was kind of current, topical, and timely, and that's not just limited to COVID. There are flu vaccines. There are vaccines for one of the current ones. There's a problem with cholera vaccine availability because there's another outbreak going on in Haiti. And right now, globally, we're seeing the largest outbreaks of cholera that we've seen. So, well, that would merge nicely with your.
I didn't know we had a vaccine. Of course we had a treatment. It was just like.
We've had treatments, but most people don't get vaccinated for cholera.
Yeah.
But we don't have enough right now to supply the global demand. This is the highest level of circulating cholera that we've seen since like the 1800s before we had a vaccine for it.
I didn't know that.
It is. So I will let you two collaborate. I will finish filling out the paperwork this evening, and send that back to you. And awesome, cool. I'm glad you're excited about that.
All right, yes, the virus is gonna be very cool, so thank you for
Yeah.
that.
I didn't know if you might be more interested in doing that with like a cancer treatment and exactly how that would work from an immune perspective. That was another option. So.
I mean, I think just the virus. I mean, yeah, but just the virus.
Okay, virus and vaccine it is.